Okay, so we're going to go over a little bit from sections 2.1 and 2.2. This doesn't necessarily go along with our book, but I'm going to teach you a lot of stuff and you're going to like it. And then we will do some questions that pertain to the stuff that we're talking about. So as hopefully you recall from geometry, a secant line to a graph or a circle, actually you talked about it a lot with circles. It was a line that went through the circle like that. A secant line is a line that touches a graph in two places. One, two. A tangent line, remember on a circle it looked like that, if I drew a better circle, is a line that touches a graph in one place. And that comes in a lot in calculus. We're going to talk about a lot about the slope of the tangent line. So that is just a little reminder of what those two definitions are. Now let's talk about, let me just see what my next slide is for fun. Okay, let's talk about the slope of the tangent line at 1, 1. Well, the problem is we can't talk about, not the slope of the tangent line, the equation of the line tangent to the graph at 1, 1. You know that you can't write the equation of a line with just one point. You need more than one point. So in order to find the equation of the tangent line, we are going to take the tangent of a whole bunch of secant lines so that hopefully you can see that as you have more and more secant lines, let's see if I can do this. Like for instance, we'll go like that. How can I make that skinnier? Hold on, just playing around here, just bear with me. Skinnier? No. Properties. Oh, they said if I push this button I can right click. How about... oh, forget it. Anyway, if I put a whole bunch of secant lines, I will get closer and closer to the tangent line. Like if I could find the equations of those three lines, I could get a pretty good idea of what the equation of the tangent line would be. So let's figure out how to do that, which means I need to figure out how to delete these three babies. Oh, and now I have another one. Isn't this fun watching me stumble all over this program? Alright, how about edit cut? How about edit undo? Okay, so we're going to pick some points. It doesn't like me right now. Oh, that was the 0.11. Oh, there's the 0.11 again. I hope you're getting a kick out of this because it's pretty embarrassing. There we go. Now back to the 0.11. This is obviously the function y equals x squared. Hopefully that's obvious to you. And we want to know the equation of the tangent line through the point 1, 1. So we're going to find some equations of some secant lines. So let's pick the point 3, 9. And we're going to find the slope between 1, 1. Slope of secant line. And the slope of that line is clearly 4. Right? 9 minus 1, 3 minus 1. I'm not going to find all the slopes by hand because hopefully you know how to find slope by now. Then try the point 2, 4. The slope of the line between 1, 1 and 2, 4 is 3. Now those ones are pretty easy, but let's get as close to 1, 1 as we can. So let's find the slope between 1, 1 and 1.01 Now first we have to find what the y value of that will be. And the y value is 1.0201. And now the slope of that is 2.01. And now if we get even closer, 1.001, the y value is 1.002001. And if we find the slope of that, it is 2.001. So, those are all these secant lines getting closer and closer and closer to the actual tangent line. What does that mean? Well, it means that the slope, now I know I have this somewhere. Hold on, let me just go through real quick. I don't know where I put that. But anyway, let's go insert page, blank page after. Let's talk about the equation of that tangent line. So the equation of that tangent line was, it went through the point 1, 1, and the slope was 2. Right? So the equation would be y minus 1 equals 2 times x minus 1. And the way we got that, the slope of the tangent line is actually the limit of the slopes of the secant lines. We took slopes of a whole bunch of secant lines getting closer and closer and closer to this point, and their slopes were approaching 2. So it's the limit of the slope of the secant lines. Now, where does this come in? This comes in when we talk about velocity. So, where is that question from the book? I know I put it in here, but I'm going to have to do it again. Okay, I guess I didn't take a picture of it. I thought I did. But there's a question in your book that talks about a rock falling from a building using the formula y equals 16t squared. And there's some questions about instantaneous velocity and average velocity or average speed. Well, we know that velocity is never constant. It's always changing. And the average velocity between two time periods, if you're saying I drove, 300 miles at a certain, over a certain amount of time, you can find your average velocity for that trip. Distance equals rate times time. So the way we're going to talk about that is that average velocity between two time periods is actually the slope of the secant line. If you think about it and you say, I drove 10 miles in 5 minutes, and then after 30 minutes I had gone 25 miles, then you can find your average velocity by finding the slope between those 2 points. Instantaneous velocity is a little bit different. That's saying how fast were you going at exactly 3 seconds after you left. And instantaneous velocity is found, instantaneous velocity is found by using the slope of the tangent line. Now remember, we found that by getting closer and closer and closer to that time and using slopes of secant lines. So, let's try a question using 16t squared. We're going to say a rock falls off a building at this formula using this equation. And we want to know how far what do I want to know? What is its average velocity during the first 3 seconds? Well, you know that at 0 seconds it had fallen 0. Sorry, this is kind of annoying, but I don't want to insert a new page. Okay. At 0 seconds it had fallen 0, and at, what did I say, the first 3 seconds? After 3 seconds it had fallen 144. I don't know if we're talking about meters. I think we're talking about meters per second, but we'll just say 144 or whatever. So, and this is the average velocity first 3 seconds. So its average velocity for the first 3 seconds is the slope between these 2 points, which is 144 divided by 3, which is 48, I think it's meters per second. We'll call this meters in seconds. Meters per second. Now the instantaneous velocity at 3 seconds, at t equals 3, is a little bit different. That's the slope of the tangent lines, of the slope of the secant lines. The limit of the slope of the secants is how you're going to find this. So we're going to check the point. We have 3 144. We know that's exact. But we want to know what happened as you approach that. So like 3.00, sorry, how about 3.1? And then 3.01, and then 3.001. Let's find the y values for those 3 x values. So we're just going to plug it into here. So 3.1 squared times 16 is 153.76. .01 squared times 16, 144.9616. 3.001 squared times 16, 144.096016. Hopefully you're seeing that you're getting closer and closer to 144 meters per second. Now, if you're not convinced, what I would like you to do is go into y equals and type 16x squared. Then I want you to push second table set. We're going to set up your table to show you these values. And we're going to start at 3. And we're going to do change in table is 0.001. And then we're going to look at the table. And as you can see, as you're getting closer and closer and closer to 3, you're getting closer and closer and closer to 144 meters per second. So your instantaneous velocity would be 144 meters per second. That's all I want to talk about as far as average velocity and instantaneous velocity. We're going to go now to finding a limit of a graphic, finding the limit of a function graphically. Now, here we have the function y equals x squared. And we want to talk about what happens to the limit of x approaching 1. Meaning, as you go along this graph and x gets closer and closer and closer to 1, which is right here, what is the value of the graph? So if we come from this way, we're getting closer and closer and closer to 1 on the y-axis as well. And as we come down this way, we're getting closer and closer and closer to 1 on the y-axis. So the limit of x squared as x approaches 1 is 1. On this one, we want to know what's the limit, and the equation is 2x plus 3. What's the limit of 2x plus 3 as x approaches 0? And you can see from the left, as we get closer and closer and closer to 0, the function goes to 3. From the right, as x gets closer and closer and closer to 0, the function goes to 3. So the limit as x approaches 0 of 2x plus 3 is 3. Now this is where it starts to get tricky, and this is where I'm going to say it probably 100 times. the limit from the left and the limit from the right must be the same. They must be equal in order for the limit to exist. So let's talk about the limit. Let's see if I have another slide. Yeah. The limit as x approaches 0. Now, we can't go from the left because the graph isn't defined from the left. So we can only go from the right. And as x approaches 0 from the right, the limit is 1. As x approaches 1 from the left, if we trace this graph and get closer and closer and closer to 1 from the left, we're getting closer and closer and closer to y equals 0. The problem is if we get closer and closer to 1 from the right, we get closer to y equals 1. 0 and 1 are clearly not equal, so this limit does not exist. The limit does not exist. Okay, how about 2? As we approach 2 from the left, we're getting closer and closer to y equals 1. As we approach 2 from the right, we're getting closer and closer to y equals 1. However, the value of 2, the x value of 2, does not equal 1. The x value of 2 actually equals 2, but that doesn't matter. The limit is what you're approaching, not what you equal. So since from the left it equals 1, and from the right it equals 1, we can say that the limit as x approaches 2 equals 1. How about as the limit as x approaches 3? From the left it's 2, from the right it's 2, so the value is 2. I hope that makes sense. Even though there's a hole, since the limit from the left and the limit from the right are equal, the limit is 1. We're going to look at another one. Which of the following statements about this function is not true? Well, first we have to draw the function. So from 0 to 1, that's from here to here, the graph is 2x. So it goes open circle there, connect the dots. When x equals 1, y equals 1. And from 1 to 2, from here to here, the graph is negative x plus 3. So that looks like this. Is that right? Hold on, let me think about that for a minute. I need a slope of negative 1, so down 1 over 1. Oh no, it goes right there. Negative x plus 3, between 1 and 2. So, let's see which one. F of 1 does not exist? Well, that's not true. F of 1 is 1. The limit as x approaches 0 from the right exists. Sure, the limit as x approaches 0 from the right is 0. The limit as x approaches 2 from the left. As x approaches 2 from the left, it's 2. The limit as x approaches 1. Oh, sorry, back up. The limit as x approaches 2 from the left is 1, because that's getting closer and closer to x equals 2, it's 1. The limit of x approaches 1 of f of x exists from the left. So, limit as x approaches 1 from the left of f of x is 2. The limit as x approaches 1 from the right of f of x is 2. So it does exist because they're both the same. Now, letter E says, oh, we already determined which one was not true. We said f of 1 does exist because it's 1. So A is not the answer, but let's keep going. The limit as x approaches 1, we said was 2. That does not equal f of 1, which is 1. That is also true. So these 4 statements are all true, and A is the one that is not true. Okay, so let's talk about these limits. This is how we're going to talk about a limit graphically. Okay, we're going to look at the graph and determine the limit. The line 2x plus 1, as we approach 3 from the left, it looks like it is 7. And as we approach 3 from the right, it also appears to be 7. So the limit as x approaches 3 of 2x plus 1 is 7. Let's talk about the sine graph. As x approaches 0 from the left, it appears to be 0. As x approaches 0 from the right, it is also 0. So the limit is, it exists, and it is 0. Let's keep going. This is a graph of 1 over x. Now, I gave you this graph in your notes to be nice, but you have to know these two graphs, what they look like by heart. So the limit as x approaches 0 of 1 over x. So let's start from the left. As we get closer and closer to x equals 0, the limit from the left, the limit as x approaches 0 from the left is, it goes all the way and all the way down to negative infinity. The limit as x approaches 0 from the right is positive infinity. Therefore, the limit as x approaches 0 of 1 over x does not exist. Now, the limit as x approaches infinity. Well, that's a different story because you can only approach infinity from the left. You can't approach infinity from the right. So all we're looking at is as x gets really, 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 really big, the limit goes to 0. The limit as x approaches 0 of 1 over x squared. Well, from the left, as x approaches 0, it's positive infinity. From the right, as x approaches 0, it's also positive infinity. So the limit exists since they're the same, and the limit is positive infinity. As x approaches 0 for ln of x, again, another graph that you have to know. 1 over x squared you don't have to know by heart. ln of x you do. As x approaches 0, now we can't approach it from the left because there's no graph. From the right we can approach it, and it's actually negative infinity. Now this one's tricky because when x equals 1, this function is not defined. But it's defined everywhere else, and it actually turns into the line y equals 1 with a hole. Hopefully you learned that in pre-calculus. There's a hole at the point 1, 1. So the limit as x approaches 1 from the left, it's getting closer and closer and closer to 1. From the right, it's also getting closer and closer and closer to 1. So the limit as x approaches 1 is 1, even though the function is not defined at x equals 1. Okay, so here's a few more examples of, we want to talk about the limit as x approaches negative 2, even though there's an asymptote at negative 2. But as we approach negative 2 from the left, the limit is negative infinity. As we approach negative 2 from the right, the limit is positive infinity. So this limit does not exist. ln of x, we just did this one. As x approaches 0 is negative infinity. I'm not sure why that's on here again. Oh, because we're talking about even though the function's not defined, you can't take the ln of 0. So it's not defined there, but there's still a limit. Okay, so here's a little recap of it, everything we just talked about. If the limit of x approaches a of f of x is infinity or negative infinity, then x equals a is a vertical asymptote. And you can see that in these last two slides. The limit as x approaches 0 is negative infinity, x equals 0 is a vertical asymptote. And it also says, okay, that's enough of that. The limit can be an asymptote, a hole, or a point. As long as the function is continuous, there can be a point that is the limit. The limit does not exist. This is the key right here. The limit does not exist if the limit from the left and the limit from the right are not equal. The limit's what you're approaching, not necessarily the y value at that point. One more slide, I think. I think this is it. Yeah. Okay. So the line y equals b has a horizontal asymptote if either the limit as x approaches infinity is b, or the limit as x approaches negative infinity is b. If that is the case, then there's a horizontal asymptote at that point. So here's the graph of f of x equals 2x minus 1 over the absolute value of x minus 3. And as x approaches infinity, you can see that the graph approaches y equals 2. So the limit as x approaches infinity is 2. The limit as x approaches negative infinity is negative 2. Now some of you are thinking, well, we can only see this much of the graph. How do we know it never, ever, ever touches it? And this is one of those graphs that you would be doing on your calculator. So you can change your viewing window to 1,000, x from negative 1,000 to 1,000, and you'll see that it gets closer and closer and closer, but never crosses the line y equals negative 2 or y equals 2. So identify all horizontal asymptotes. There would be a horizontal asymptote at 2 and a horizontal asymptote at -2. Okay, there's two horizontal asymptotes because as x approaches infinity, y equals a constant. Okay, I guess that's all for now. Your next slide will be on your next video will be on direct substitution.